Okay, so let's start the lecture. So today is a little different. We're going to talk about sorting algorithm, and there is another exercise at the end. Although this one is more difficult, so we'll try to go through that. But I think this is something that probably you'll have to review after class. Because it's a more complicated algorithm, and there's more to be done. But the first part of the class is just about reviewing. Discussing sorting algorithms and how they can be implemented on a shared memory machine. So first, there was a discussion about array reduction. So for the homework, you should not do array reduction. So yeah, just be careful about that. Everything is just scalar. But array reduction is an option in recent OpenMP. So I was just sort of curious about it. So I kind of looked it up. So you have an example online with reduction array of CPP here. And so this is just one line from this example. So if you look here, so this is not a terribly meaningful example, because if you look at the way this is written, you're basically doing a sum over all entries in a column. Okay. If you were to write the J loop outside, and just the I loop inside, then in fact, no reduction is required because this entry will be local to a thread. But say maybe you want to do the loops in this order because, for example, in terms of memory access, it's preferable for B. Okay, so if you do that. Then you're going to have threads doing different I's, basically looking at different rows, but contributing to the same column. Okay, so there's a reduction on AJ, and so you can specify reduction, with an array with reduction plus and then the array. So the syntax is you can just say just the array, okay, and then it would be if it can figure out the size. Then it will just use the array with its size. Otherwise, you need to specify, the indices in the array that, for which the reduction needs to occur. So perhaps it can deduce the size. The compiler can deduce the size, but if not, then you need to specify, the starting and ending index. 0 is the default, and the syntax for that is. So actually, this is a little confusing. This is actually not the starting and ending index. Okay, actually the last index is n-1. So the syntax is actually starting index, but then this is the length. This is how many entries you want to process starting from 0. Okay, so the syntax is a little weird. It's not like the usual maybe MATLAB or Python syntax. It's basically lower bound when you start, how many entries you want to look at, and then if there is potentially a stride. Okay. And the actual formula goes like this. So you start with some lower bound index, LB, and then you have this stride. So the next one will be LB plus S, LB plus 2S, LB plus 3S, and so on. And you're going to pick n entries, right? So you start essentially at 0, and then n minus 1 times S. So you can see that n is also it's definitely not the address of the final entry, because it's you have to count for the stride. Okay, so for example, if you say A is your n, that's all the entries in A, if n is the size, and then here you say n over 2 is 2. So if you have a stride of 2, okay, then there's going to be n over 2 entries that you need to consider. So you could pick all the even entries, with this type of notation. Okay. All right. So this is just kind of a short recap on doing reductions with arrays. So it's a new feature of OpenMP, and it can be convenient. But there is again a non-trivial cost doing that. Okay. If you look at the previous cost or the previous code that I wrote, what's happening is in order to do this reduction, there's no magic. Okay, you have to make multiple copies of A. So each thread will have its own copy of the vector. Okay, so that potentially quite a bit of memory allocation. And then you do this reduction in all the local copies, and then once you're done, you have to take all the local copies add them up together. So let's say you have 4 threads, then you're going to have 4 partial copies that need to be added up, and then you get the final result. Also, mind you, just as a sort of a note, you know, a memory allocation in multi-threaded codes is has very bad performance. Okay, it's a very expensive, slow operation, and if you have multiple threads that make memory requests, you really can slow the system down a lot. So that's something to really pay attention to. In parallel codes, it's very common to sort of ahead of time try to allocate all memory that will be required, and then you sort of start the calculation, because you know doing sort of memory allocation as you go is typically you know very poor, will give you very poor performance. So as best as possible, try to figure out how much memory you need, kind of allocate, and then sort of work with that. Okay, that's typically a better strategy. Okay. All right. So any question about this array reduction? So it's just sort of a wrap up of Wednesday's lecture. Okay. So let's talk about sorting algorithm. Sorting algorithm, it's you know, it's I guess a specialty in computer science. You're not graduating from computer science without hearing about sorting algorithms. And here I'm going to just give you an overview of you know some of the common sorting algorithms, and trying to focus a little bit on you know how you would implement those algorithms on shared memory computers and what are sort of the challenges. So you know, homework 2 is you know basically looks at this problem, focuses on radix sort, you know, which is you know actually not that simple to implement as you're probably realizing now. So it's relatively you know reasonably simple in sequential, but when you go parallel, you know there's a lot of difficulty. So I'm not going to go too you know much over that, because you know you guys are kind of working on it now. So it's obviously restricted to just integers or floats, so things that basically can be expressed with bits. Okay, so it uses this concept of buckets, and so the idea is you look at the bit representation of all the numbers, and then you split all the bits into smaller groups. So for example, if you have groups of 3 bits, then looking at 3 bits, you can, you know, that gives you a number between 0 and 7, okay? And so what you do is then you create 8 buckets, and then based on these bits, you can sort all the numbers, you know, in the corresponding bucket, okay? And so, and then you repeatedly do that by essentially looping over all the bit groups, okay, until you've covered all the bits. And so if you do this correctly, you get, you know, you end up with a nice sorted array. So I'm going to use these videos. Oh yeah, I need the sound. I didn't check that. Sorry about that. So definitely need the sound. That one. I don't know if this is going to work. Maybe there's no sound in this room actually. Well, let's see what happens. Actually, I probably can use the sound on my computer.
Oh, this one.
So I guess I'll have to do that. I'm not sure what's wrong with the. With this thing. Well, it wasn't working the last time, so I have to assume that indeed the sound is not working. Okay, let me just see if I can redo the HDMI thing. Okay, so I guess the sound is not working, so let me just try to give you the sound of my computer. Not as great, but actually with the mic here, it might work out to be pretty loud. Okay, let's try that. The sound maximum. Well, the sound is actually not super informative. But it's fine. So the sound has to do with, just basically the bigger the number, the taller the bar, the higher the sound. Okay, and when you do radix sort, okay, so I want to this thing here, to play. Right. So when you do ready sort, you have two options that are actually rather different. One is you can start with the high bits, so the most significant digits, like the biggest numbers in some sense. And then the other option is LSD, the lowest significant digit. So here, this one is sort of easier to comprehend. So basically, the first pass is going to give you these buckets from roughly small numbers to large numbers, and essentially inside each bucket, you're not sorted. Okay, so we're going to restart this, but basically, when you start, everything, so nothing is sorted, and then just keep going like this. So after a couple of passes, okay, like right around here, for example, then you see the high bits are kind of sorted, and now you're doing a pass over the lower bits. Now the trick is the sorting is so-called stable. So basically, if you have two numbers that are sort of equal in input, the output maintains the same order. Okay, so essentially, what this is saying is, for example, if you look at all the numbers in the high bits, and then you sort according to the low bits, then the guys who have the same high bits, okay, in some sense equal for the high bits, will sort of stay together at the next pass. But then on top of that, you do a sort on the low bits. Okay. So this one is sort of easier to comprehend. Okay, it's fun to watch. But it's actually a little bit more difficult to implement because you need to look at each bucket in turn and do this sort on the lower bits inside each bucket. Okay, you cannot fix the buckets. So this is it. And then if you look at the other, so the other one is the least significant digit. So this one is actually way trickier to comprehend. But it's actually easier because you start by sorting with the lowest bits, and then you resort with the next set of higher bits and so on, and just keep going like this. And right, and so it just you keep repeating this sort. So this is basically what you're doing in your homework. What you're doing is basically the least significant Quicksort. Progressively sorting by higher and higher bits. So of course it looks completely random because only at the very end, for example, you can see how now you have, well, it's actually very hard to see. But you could basically need to ignore it's basically impossible to really make sense of this because really only at the end when you sort the high bits do you actually see the sorting sort of materializing. Right, so for example, if you stop here, can you make sense of this? Well, yeah, so what's happening is basically these numbers being sorted on the low bits are nearly equal except for the high bits. Okay, so this is why you have this huge jump, which is basically more or less n over 2 or something like this. And so then and so now you're sorting by the high bits. Okay, so we're going to look at different sorts. So this is the one for your homework. Okay, I'm just going to leave it like that. So there's a number of classical sorts. So number one is Quicksort. Number two is Mergesort. So the Quicksort is probably one of the most famous algorithm. I don't know exactly if this is the most widely used. Well, typically the fastest algorithms are a combination of different strategies, Quicksort, Mergesort, and maybe other sorts that you combine at different stages, to really, get highest performance. So Quicksort is doing is actually very, very fast, very, very good. It has a bad worst case situation. I mean, it depends on exactly what sort of Quicksort you're looking at. The basic Quicksort is a very bad worst case. It can be, you can improve. But curiously, for example, in the vanilla implementation, if the input array is already sorted, it actually takes n squared to verify that it's sorted. So that's really that. Whereas for most arrays, the cost is just n log n. So the idea of quicksort, so anybody familiar with quicksort? You can raise your hand. Okay, so maybe half, yeah. So the idea is actually very, very simple, although the efficient implementation is more challenging. So you just pick more or less a random entry, or you can be more clever, but so it can be the first one, the middle one, last one, you know. So you pick an entry, and then the first pass is just you're going to go over the data and simply separate all the points that are lower than the entry you picked, and all the entries that are larger. Okay, so you basically just get two groups. Okay, and then you're going to take each. So of course, all the entries in the first group are lower than the entries in the second group at that point, right? Because they're all either small in the pivot or large in the pivot. So now you take each subsequence and just repeat the process until everything is sorted. Mind you, that's actually a very good strategy for humans. If you have a pile that you're trying to sort, it's actually a very good strategy. Right? Because you can just pick, you want to sort papers according to grades. You pick the first paper and then you just make two piles, below that grades, higher the grade, and just keep repeating. So it's actually very good for humans as well. The merge sort is rather terrible for humans, but this one is actually quite good. Okay, so this is an example of a strategy here. So for example, the pivot is shown in blue, and there are different. So the nice thing is the sort is done in place. That is, you do not need special temporary storage for the sort, right? You just work with the original storage. So this is very important. Merge sort typically requires, the array sort extra storage. Although again, you have more efficient implementation. Let's not do that, but more complicated. So the basic implementation requires extra storage, but here not the case. So you start from 3, and then you want to loop through all the entries and separate on the left all the entries lower than 3, and on the right all the entries larger than 3. So so I guess the first example is completely boring because somehow 3 is the smallest entry. So okay, it's already done. So you do nothing. So actually, that's kind of a weird example actually. So here you have two subsequences, except that one subsequence is basically just 3, and the other subsequence is the original set of numbers. Although actually, this case is actually interesting because you see, well, the first step actually didn't do anything, right? It didn't do anything, but it does require n operations to make sure that all entries are actually greater than 3. So this is how you get the worst case scenario. You can see if your body is sorted, then 3 takes n operation, but the next step will take n minus 1, n minus 2, n squared. So this is completely silly. But that's the worst case scenario. So let's look at 156, which is kind of more interesting. So this one, actually just takes, so you have to keep looking until, while blue is 156, so basically it takes 4 stages, more or less. So what's actually shown is the number of swaps. So you're looping through your entries, and you're looking at whether you're encountering entries that are lower than 156. So the first 156, okay, that's fine, it's already on the left. Then you look 205, that's greater. 93 is lower, right? So it needs to be on the left of 205, so you flip. And then you just keep going until you hit, actually towards the end, 126, and then you're going to flip it with 205. Okay, so you end up with this, 126, and then I think you're done. Right. So you're done after that. Sorry?
It's a question about the visualization. So each row is a step in the process, if I understand.
Well, yeah, more or less. I mean, it's not exactly a step because, for example, the second row is actually checking all the entries. But basically, nothing is sort of happening, so there's nothing to visualize. So for example, every swap is basically creates a new row. Right? Because you have to do it in place. So you have to be a little careful how you do it. You cannot just loop and write out all the entries lower and all the entries greater. You've got to do it in place. So you traverse left to right, and you do these swaps in order to get the output you want. So you have to record, for example, the way, for example, 126 goes here is because I recorded then 205 was the beginning of the larger than section. Okay, so when you encounter 126, then basically you move 126 instead of 205, move 205 instead of 126, and then move this pointer for the larger than section one more. So that if you encounter another entry smaller than the pivot, you can swap again and so on. So there's a bunch of counters that move around like this to see where the swap needs to be done.
I see. And you don't want to swap every single entry that's lower because that's expensive?
No, that's right. Every time you encounter lower than, there's a swap. And
it doesn't look like 156 and 56 are being swapped until much later.
Okay, all right. So that row is different. That row is actually you're done with that sorting, so to speak, but you have to place the pivot at the right location. So actually the 156 is then swapped with the last entry in the lower than, so that now it's in the right position. Because the pivot is supposed to be in the middle.
Right. But I don't.
So this is what you're seeing here. And now you're done. And now here you're sorting the left, and here you're sorting the right.
But between the third and fourth row, for example,
right.
Wouldn't I expect 156 to be swapped with 56?
No. 126 is swapped with, well, I don't want to spend too much time on that. But 126 is swapped, no, it has to be swapped. 126 is smaller than 156. So the way it works is you look at where the larger than section begins. It begins at 205. And you always swap with, so let me draw it here. So you have the lower than section and the larger than section. Okay, let's say here you find a lower than. Okay, so it's in the wrong position. So the way the swap occurs is it goes like this. You take this one, which is a larger than, you put it here, so that's fine. You take this one, which is a lower than, you put it here, and essentially you move that block by one, or rather the pointer, to the leftmost entry in the larger than just is incremented by one. So just keep going like this. So and so that entry keeps being bumped to the right pretty far, but like who cares, And then you just keep inserting the lower than like this. You get the.
I understand. I don't see how that visualization implements that. But that's
okay.
Fine.
Okay. Yeah, all right, so maybe I can explain after the class. So supposedly this visualization is showing you that, but maybe this is not working. But essentially the red entry is so let's see. Right, the red entry is basically the entries being swapped. So 56, there's nothing because it's already on the left. Then the 93 is swapped with 205, and then the 126 is swapped with the 205. And then the 156, 126 are, this is positioning the pivot, and then you just repeat it. Yeah, I guess the only line that's vaguely suspicious is the third one, because here you're just looking at the first entry, and in some sense you're not doing anything here. Well, anyways, okay. All right, so this is what I want to, this is the Python code. So I'll just kind of, go over that quickly. But so basically, just traversing your array, and wherever you find that you have a lower than entry, so smaller than pivot, right? Whenever you encounter it, then you swap it with the current greater than location, so basically this number here, you swap it and then you increment by one. And then here this is basically inserting the pivot at the right location, and then just repeating the quicksort with the left and the right. So okay, so gotta show you some more of these animations for the fun. So it went very fast. This is why this is kind of a preferred algorithm. No additional memory, relatively easy to implement. But it has a very bad worst-case scenario, although this can be fixed. So there's a bunch of so there's basically different ways of doing this, and they all vary by how how you're doing the swaps. Okay, so like which pointers you use to do the swaps. So here you using left pointers is basically what I just described, where you keep going, and whenever you find something lower than the pivot, you swap, and this is noting where the greater than block starts. Okay, so boom. So here you see, here you get all the entries lower than pivot, larger than pivot, and then you restart. Again here. So this is the pivot, and here this is the beginning of the greater than, and this is searching for the lower than. Okay, and just keep going like this. So this one is basically just what I explained. Just move forward, and then you insert the pivot. Okay. So it's a little tricky to see because now you're actually sorting subsequences. Right, so here you're sorting here. And then once you're done with the left side, then you're semi-sorted with the rest, but now you need to kind of look at all the sub-sequences and recurse down. So it's an n-log n strategy. All right. Always satisfaction when it finishes, right? Feels like, wow. Done. Okay, so this one is basically more or less the same strategy, same thing, but using pointers from the right and left. So you're moving right, left, and swapping whenever needed. And so the pivot is maybe taken in the middle, okay, which is not necessarily a better choice because it depends, how things are distributed. But sort of makes more sense in this context here. But the strategy otherwise is the same thing. So it's just basically doing the swaps in a different manner, but the strategy otherwise is exactly the same. All right. And then last one is actually the last one. So that's actually more trickier to figure out what it is. So this one is sort of special, but it's kind of interesting. So this one is a special case where you're sorting, so it's still a Quicksort. It's actually a Quicksort with basically left and right pointers. But here there's this assumption that a lot of elements somehow are equal. So there's a little optimization for the case where entries are equal. And so there are separate pointers that look at entries that are equal to the pivot and track entries that are equal to the pivot. So that's why when you start, these are the yellow entries. And so when you start, you see these, a weird distribution in x cube, to get a lot of equals in the middle. But you can see here, for example, when you start, you can see how all the guys equal to the pivot, accumulate at both ends. While in the middle, the other pointers look at the strictly and strictly small and strictly greater than. Yeah. Questions or? Yeah. So, but essentially it's the same as before. And so once you're done, then you have to, all the equal need to be inserted in the center. So this is a good strategy when you have a lot of equals. And then you insert equals. Depending on the properties of your distribution, some of these methods, if you have some trends, if things are not completely random, but there's some trend, then some of these strategies are, are superior. Okay. All right. So, like I mentioned, n square and so on. And so this one is not stable. If you look at the elements that are equal, typically they can be reshuffled in different ways, right? But you have variants that make this, well, this is really not that easy to see. A little bit. So this is showing how to, actually, take off maybe. Oh wow, this is not that great. A little bit bigger. So this is showing, how you would go about doing a quick sort in parallel. Actually, a lot of these ideas are going to be very familiar to the method techniques you're using in homework 2. Okay, so all these methods, have the same sort of difficulties in terms of parallel implementation, so they come up with the same solutions. So here the idea is, okay, so you want to do a quick sort, okay, and the way you're going to do that is first you need to select a pivot, okay. So you could say, well, it's going to be the first entry in the array, okay. So 7. So if you're in shared memory, you don't have to do anything, okay. So everybody has this value 7. Maybe you make a local copy or whatever, but everybody knows the pivot is 7. And so you then take the input at the top, subdivide across the different cores, and then simply each core is going to do a quick sort, or it's going to do a lower than and a greater than on just a subset of the entries. Okay, so you get the gray and white, and so then the next step is to so this is actually shown on the next slide. Next step is to then have a global rearrangement. Okay, so this is similar to what you're doing in homework 2. So essentially, this can be done in parallel, except you need to know each thread needs to know where to write its gray and its white entries, like what's the starting index. Okay, so there's again some histogram and some scan that need to be done. But then essentially after that it's just a repeat. Okay, now you have the left subsection, right subsection. So you assign a subset of the cores to each subsection. You have a pivot, you have a local quick sort, and then there is a merge between P0, P1, and P2, P3, P4, and just keep repeating. Okay, so as you go, lower in the algorithm, it becomes more and more parallel. For example, here, each core has its, well, maybe not exactly here, but okay. Towards the end here, each core has its own subsection that is sorting, and things are quite fast. So one difficulty you immediately see is that in Quicksort, it's very hard to control the size of these subsections. It can be super uneven. Okay, so there's a load balancing problem. So basically, every time you have some of these subsequences, you need to figure out how many processes to assign to each subsection, and this may lead to load imbalance. For example, here, only 2 and 3 still have work to do. The others are done at that stage. So there's some load balancing issue. And so looking at just the first step, which is going from local to global rearrangement. Okay, so here is basically where there's difficulty. But this is, again, just exactly like in homework 2, just a question. In homework 2, you have the local histogram, the global histogram, and the scan. So here it's the same idea. You just want to figure out where you should write your entries. So for example, P0 has 7, 2, goes here. P1 just has 1, goes here. P2 has 6, goes here. P3 has 3, 4. P4 has 5. So for example, looking at P4, the only thing it needs to know is what's the index for its own entry. So basically all the processes just count how many gray they have, how many white they have. So this is how many gray they have, how many white they have. You do a prefix sum. Okay, so this is actually exactly where you need to write your gray. Index 0, index 2, index 3, index 4, index 6. Last one is skip. And this is actually where you start the white entries. So here you have a prefix sum. Okay, so you need to add the 7. Okay, so it's not shown here, but you need to add the 7. So for example, 7 plus 0 is where you start writing the first white. And 7 plus 2 is when you write 17, which is the white for P1. And then P2 is 10. So this is entry 12. 7 plus 5 and so on. So you can see that with a little bit of bookkeeping, then you can make this nice and parallel. There are a couple of steps that are a little tricky. For example, the prefix sum, but it's not too bad because the prefix sum, you need to do this on basically P entries if you have P cores, so it's independent of the size of the array n. And prefix sum is a classic algorithm that can be accelerated. Fastest time is basically log P passes. So it can be done pretty fast, but in practice, On multiple processors, you don't have that many cores or threads, so you can just have one thread do a prefix sum, and this goes extremely fast. On GPUs, it's more expensive, and you have to be a little bit more careful. But here, this can be done easily. Okay, so let's move on. Second. So second is Mergesort. So Mergesort is actually conceptually is somewhat simpler algorithm. It's for humans it's not super easy to use, but for a computer it works pretty well, and so it has actually it is in some sense slightly less efficient than Quicksort. But it does you can avoid this worst case scenario, right? If your vector is already sorted, essentially Mergesort is still n log n. The cost is basically more or less fixed, so it's very, very fast. So the idea is Mergesort is very simple. It just consists in observing that if you have two sequences that are sorted, then it's relatively easy to merge them into just one bigger sequence that is sorted. Okay, and the idea is so works as follows. So let me just show you on this example here. So initially, you basically don't do anything. You just split your input into a binary tree. Okay, so it's basically a recursive call. And then you get to just very short vectors. So it could be here one, or maybe just a small vector. Actually, you could use another strategy to sort these small vectors. But here, you're going down to just one entry. So of course, one entry in some sense you're already sorted. There's nothing to be done here. And now you reach the merge step. So merge step is basically the first step is just to grab the mean and max of these two entries. Okay, so it's kind of trivial. And then you want to do a merge here. So the idea of the merge is you have two pointers, right, that are going to be moving, and you decide, what's the minimum. Okay, so you find the minimum is 3. Okay, you insert and then you move by 1. Okay, the minimum is 27. You insert and then you move by 1. Minimum is 38. You insert and you're done. And so last entry. Okay. So basically, you have these two pointers, and you keep moving, and each time you pick the min, you insert. And you move that pointer by 1. Okay, so you just keep grabbing the minimum, and eventually, you have merged all the entries. Just keep going, until everything is sorted. So you see, it's very, it's a very nice sort. Well, it's very balanced because the splitting is very regular, right? It's basically you deviate by close to 1, right? So it's sort of a perfect binary tree here, and so you get this nice n log n and so on. So it's quite efficient. So gotta show you the little music here. So basically, you see, you're just creating small sorted arrays and then merging by using these two pointers. Now you're going to create another kind of long sorted array, and then you're going to go like this and merge these two together. All right, so some points going to go from here, right? So right here, right? And doing the min max, and so on, and boom. And then you just repeat this. So when I showed you, I was going top to bottom, and here it's more like left to right, but it's the same idea. So actually, I'm not sure what exactly it's doing here. It's going through the entry, but I'm not actually doing anything. So this is kind of a visualization thing. Because technically, as you're moving, you're obviously sorting. Okay. Oh yeah, I know what's happening. It's because it's basically there's a problem with there's probably a problem with being in place, It's probably, there's a trick to making it in place, which is probably not what's shown here. And so there's a copy of the vector being made. Might be what's happening. So that's why it's sort of doing this in two phases. It's actually doing it first and copying somewhere else, and then just showing you the result. Okay. So anyways, all right. So this is Mergesort. So merge is actually a very tricky business. If you think about it, the merge is very nasty. Okay, because the merge is a completely sequential process, right? You move left to right, and how do you parallelize this? So when you start, initially you work with a lot of very small sequences. Okay, so you just split these subsequences, you have a lot of mergers, a lot of parallel work. But towards the end, you end up with these very large sorted blocks that need to be merged. So imagine, for example, that at the end you just have two sorted subsequences. Okay, you want to do a merge, or in principle you have two pointers that need to move. And it's not obvious. There's no obvious way to parallelize this. So there is a trick. It's not a perfect trick. It's always a trade-off. But the idea is basically to it's actually basically a type of of quicksort a little bit. So you're going to take one of the subsequences. So let's say here you're trying to merge P1 R1 with P2 R2. Okay, so it's sort of a general merge, where you have two subsequences at some location in the array. You want to merge them. And the idea is to do a little bit like Quicksort. You're going to take the left one, and you're going to pick a random entry, so maybe the middle one, X. So now, having picked X, there is a fast algorithm here to find out, basically like a log n algorithm to find, because this is sorted, to find where is X, where the lower than X here and the greater than X here. Okay, so this is fast. So just log n. So here actually everything is still sequential, but it's log n, so like tolerable. And then after that, now you're fine because the lower than x can be merged with the greater than x. I'm sorry, the lower than x here can be merged with the lower than x over there, and then the greater than x can be merged with the greater than x. Okay. The only thing you need to know is where this point is, but since you know how many lower than you have, then you know exactly where to insert this, and then you can just do, this is a sequential merge on one core, not a sequential merge on another core, so you can have the two cores just working. So, so that's a good strategy. Obviously, it depends on this thing being balanced. Okay, so for example, if this is split in exactly two, then you're fine. But if this is super uneven, then it means that one of the cores is going to be done faster than the other. So you always have this type of trade-off. So the performance, you have again the worst case, the best case, the average case, and you may have then various optimizations kind of around that. Okay, and so just to sort of wrap up. So I'm just going to, and then I want to move to the exercise with the Bionic sort. So you have a variant of radix, which is basically bucket and sample sort. So I'm just going to go quickly over that, just as sort of illustration. So bucket is basically just a variant of radix. It's not the same algorithm, but it's kind of the same spirit. So the idea is it's actually even more simpler than radix. Let's say you want to sort integers or you want to sort floating point numbers. So it only works for numbers because you need this concept of intervals. And you need to know the smallest and largest. Okay, so some stuff to be done there, but let's say you know what the smallest and largest is, so you're in this interval AB. So now what you do is you take AB, you're going to split it into P sub-intervals, okay? Then, similar to radix sort, you can sort your input into all these buckets between A and B. And then you have P independent buckets, and now you just sort inside each bucket. Okay, so this is a strategy. So actually, if you do the radix sort, I could have asked you to do a similar thing. If you do the most significant digit, so what you have is the least significant digit, but if you do the most significant digit, then you can start, this is basically the same process. You start with the largest bits, sort into bucket, and then after that, it's just sorting each bucket using the other bits. But this can be done in parallel, where each thread does a different bucket. Okay, and so of course the problem is, well, how do you figure out in an efficient, a good set of buckets? If you have A, B, you can split into buckets of equal sizes, but some of these buckets might be empty and other buckets might be full. Okay, so there's a lot of, again, load imbalance because of the uneven filling of the buckets. And so split or sort is a strategy that tries to overcome that. Basically, it tries to figure out what are the optimal intervals. So it's actually intervals such that the number of entries in each interval is about the same. So it's roughly n over p. So the way this works is actually not that bad. Of course, it's always a heuristic because you have to balance communication and the sequential steps with sort of efficiency, essentially this load imbalance. So what you do is, so each core, each process starts again as usual with a subset of the input entries, and then the first step is just to figure out what these intervals are. Okay, and after that it's basically just the regular bucket sort. And the way to do that is, well, each process independently figure out their own intervals so that it spreads exactly equally. So for example, for P0, you have 3 entries in the first bucket, 3 entries in the second bucket, 2 entries at the end. Here 3, 3, 2. Here 3, 3, 2. So everybody 3, 3, 2. Okay. So so you find the so-called splitters of these entries here, such that your inputs are evenly split. Okay, across each interval. And now, so these are the local splitters, but you want global splitters. But so the idea is, you're going to actually collect all the splitters that you've computed so far and split that again. Okay, and hopefully this actually works reasonably well. So you gather all the splitters. So now you have, the number of entries here. So maybe you have p subintervals, and so like p, these sections, and then p buckets. So maybe you have p square entries roughly here. So now, in all those entries, again, you look for splitters, and these are going to be the final global splitters to be used. Okay? So once you have the final global splitters, then you go as before. So everybody just sort by bucket according to those splitters, and then you do the cystogram, and then you do global rearrangement. You create p buckets, and then once you have everything sorted into these p buckets, then each process just works on one bucket and sort within its bucket. Okay. So just a variance of sort of radix and bucket sorting, but where you sort of optimize the choice of intervals. Okay, so basically this sort of wraps up the sorting algorithms, and the last one is going to be the Bionic sort, and that's the one that that's going to be working on a little bit. Yeah.
How are the samples selected in this case? Like 7 and 17 and P0?
You mean the 8 and 17? Which samples?
The local samples, 7 and 17.
Oh, so 7 and 17 basically here P0 is going to well, it's on the face of it sounds pretty bad, but in parallel it works pretty well. So what you do is you sort your own entries, okay? And then once you sorted your own entries, essentially you look at index 0, 1, 2, 3, 4, 5, so 2 and 5, and these are your splitters, right? But the point is, this is a sort and it's expensive, but this is completely parallel, right? So this goes presumably fast. Once you have your splitters, then you collect, okay, and then you split this again. So this is a sequential step. Now that taking those global splitters is sequential, and then everybody uses that. So that's okay, yeah.
So you select the splitters, and then based on that, you.
So you select local splitters, assemble that. These are all the local splitters, and then select the splitters for that group, and hopefully those splitters are good for the original set, right? Like these local splitters split evenly in each local set, and here, obviously split evenly as well, but you're hoping that 8 and 17, So you want to split into 3 groups, like lower than 8, lower than 17, and the rest. And you're hoping that the 3 groups are even, because it's splitters and then splitters and splitters.
But then the array was initially distributed in different processors.
Right.
It was already initially distributed.
Yeah, right.
And then we want to just make that.
So you want a
distribution
global sort.
uniform.
Right, and sorry, so what was your question?
So, like in the first step,
Yeah.
the array is already distributed among processors,
Right.
Or threads.
Right.
So when we want to choose global splitters, do we want to make that distribution uniform, or do we want to actually sort it? Like, why are we doing the global splitting step when the array is already split in the first step?
Okay. So, all right. So the first splitting is perfect. Why? Because you take n entries and you just divide into p groups. Okay. So the first splitting is perfect. But what you want is you need to come up with p buckets, right? And each bucket corresponds to a given interval. Okay. And so the sort of first step in this algorithm is to take your input and put it, all the entries in the first bucket, second bucket, third bucket. After that, you can do independent sorts. Right? Actually, the step is sort of not shown here. You do an assignment and sort. So here you have the final result. So the question is, the first splitting, of course, is completely even because you do just n over p. But you need to figure out the buckets and the splitters. So that is the problem. Okay, so now I take 8, 17. So now once you pick those splitters 8, 17, then that entirely defines the buckets. And now those buckets are not actually equal, right? They're no longer n over p. Hopefully they're close to n over p, so I didn't count here. So they're pretty close, 7. So here, for example, it should be 7, but you have 2 more. And then 23, so here there's 1 more. So they're just off by 1 or 2. So they're almost exactly even. But for example, the initially P0 had 8 entries, and here only 7. So you see there's just a slight imbalance. But of course, the key thing is once you have things inside each bucket, then you can sort independently again in each bucket, and the final result is completely sorted. Right? So for example, if you look at the result of the first step, well, you sorted in each subsequence, but because you didn't use this idea of bucket and splitters, it's not a global sort. So everybody's okay with that? Okay, so let's talk about Bionic sort. So Bionic sort is a very interesting, and we'll do this little exercise, but probably won't have time to finish. But the Bionic sort is so it's at some level it's a little bit like the merge sort. So the merge sort was also sort of had this very regular process. Like Quicksort was very irregular, right? Because you get the subsequences of different lengths and so on, very regular. Merge sort was more regular, but when you do the merge, you still had these pointers that were sort of moving about at different speeds and so on. And sorting networks is a different idea. Here, the sequence of operations is always the same. So the way you're accessing data is completely deterministic. Okay, so in merge sort, for example, you had the pointers that move at different speeds. So here, no, the pointers, you always do exactly the same operations. You always reach on the same memory location, in the same order, and so on. So this can be advantages for many reasons. So actually, it was shown in a paper that, for example, on GPUs, because this was such a regular calculation, it actually turned out to be very efficient. Although that's a bit of a lie, because the original algorithm is actually not really optimal. So they had to make some changes to improve the performance that broke the regularity. Okay. But so still, it was very fast in GPUs. But an interesting thing is because everything is completely fixed, you can actually build hardware, like fixed hardware, that will do the sort. So if you have a small sequence of numbers that need to be sorted really fast, and you want to build special hardware for that, then you can do this because the flow of data and pattern is completely fixed, so you can optimize, the communication and so on to get super high performance. So this is sort of very special. So so this can be the fastest for this reason. And the only operation you have to be doing is compare and exchange. So basically, you're going to take two numbers, do comparison, and if A is smaller than B, you do nothing. Otherwise, you just swap. Okay, so it's compare and exchange. And this is the building block you're doing. And now then you're going to apply a series of these coex, but the sequence and interest to be compared is always fixed. It's completely fixed. Okay, so it's very strange. There's absolutely no. It's completely dependent of the input data, but nonetheless, at the end, everything is nice and sorted. So this is just showing you that you get very high performance. So if you're interested in this paper, GPU sorting, it's comparing Bionic sort, and they're super optimized thing with another Bionic sort, and this is a sample sort. I talked about it. This is the Quicksort, which is actually not that good because this load imbalance I was talking about. And then there is a thrust merge sort, so merge sort, and the warp sort, whatever that is, at the bottom. Of course, it completely depends on what sort of input you're getting. I mean, you can make Quicksort very fast or very slow depending on the type of input you hear. I assume that it's completely random input, but But so Bionic sort, because it's so regular, it was a very good fit for GPU. So mathematically, this is a very beautiful concept. Highly non-trivial, and it's very hard to comprehend that just a completely deterministic sequence of operation actually can lead to a correct sort. So basic concept is Bionic sequence. So you have different ways. You have more or less general definitions of Bionic sequence, but for just this application, the definition is that it's a sequence in which the first half might be increasing and then the second half is decreasing, or vice versa. Okay, so you keep having to jump between these two, so or they're descending, and then the second half is ascending. So you have this concept of Bionic sequence, okay, and this is what we're going to be using. And so here's the key thing: if you take a Bionic sequence, okay, then there is a very simple process of compare and exchange. This coex, there's a simple process of coex that will transform this Bionic sequence into two sequences where the first subsequence is smaller than the second subsequence. So it's not a perfect sort. You're going to end up with, the input is, say, a Bionic sequence, and the output will be two Bionic sequence where, the left half is always lower than the right half, okay? And then you're going to be repeating this and so on, different ways to sort it out. So this is how it works. So you can, if you're interested in this, I invite you to take a pencil and paper and sort of verify that this algorithm is correct. But so you do this Bionic compare. So what Bionic compare does is it takes as input a Bionic sequence, okay, and then it's going to output two sequences that are both Bionic, and everybody on the left will be smaller than everybody on the right, okay? And so the first half is going to be taking this min, and the second half is going to be taking the max. Okay, and here you're basically comparing the first entry and the middle one. And then next entry, and so on, until you reach one before middle and last, okay? So now you're doing min, max, and so on, so you see how beautiful this is. It means you go just left to right in the array, and if this is smaller than that, then do nothing. Otherwise, just swap. Okay, that's basically what the min-max here is going to be doing. And so you have 2 pointers that move starting from 0 and n over 2. Just keep incrementing, and if you're greater, then swap. Otherwise, do nothing. So it's just this compare and swap that you keep repeating. So here is basically, the diagram that, explains it all. So again, you're going to start like this. So 2 pointers, one at 0, one n over 2. You're going to take the min and the max here. Okay, so basically you swap if this guy is smaller than this guy. So initially there's no swap, but then what's happening is you're moving to the right. So imagine you're moving to the right, and let's just look at the min. So here it's just increasing, okay, and here it's decreasing, okay. So so when you start, so let's say that the red is min when you start, but this guy keeps increasing. So at some point, they might become equal. And when this happens, the one on the left keeps growing, the one on the right keeps shrinking. Okay. So you see that when you do this min, you'll keep selecting from the left, and then at some point you'll keep selecting from the right. Okay, and this change happens exactly when you reach a point where these two numbers are equal. Okay, and because you're doing this min, it means that all the guys on the left are going to be small and this equal. All the guys on the right are going to be greater than this equal. Okay, so first of all, everybody here is smaller than this equal value. Everybody here is larger, so you have sort of partially sorted your input. And moreover, if you look at the pattern of things, then you can convince that here it has to go just up, because basically this is a min. It has to go down, because basically it comes from this guy here, and here this is the max, so this is the reverse. So you're going to get two sort of opposite Bionic sequences, increase, decrease, and then increase, increase. So you get these two sort of opposite Bionic sequences, and then they're sort of partially sorted. Okay. So this is the compare step. Okay. So that's it. So two Bionic sequences, left is smaller than right. All right. So the details of the algorithms are quite complicated, but at some level for the exercise, you don't need to understand really all of it. So I'm going to give you some code and so on that has most of it already implemented. So you don't need to understand all the details. But the idea is to be to work as follows. You're going to start with very small Bionic sequences. So initially it's it just there's nothing to do because you just get Bionic sequence of just so 2 entries. Okay. And then you're going to take two Bionics. You're going to take a Bionic sequence of some length. Okay. Then you're going to do this compare. So you're going to so it's going to give you like the left Bionic sequence and the right, and you keep doing this compare against essentially the whole thing becomes sorted. Okay. So you're going to get something that's going up, and then after that you're going to get something that's going down. So effectively, what you did is you took two. You were able to take two Bionic subsequences and create a bigger one, a bigger Bionic sequence out of it, and just keep repeating until you're done. So this is what this looks like. So it takes a while to kind of figure it out. So you start first with sorting up, down, up, down, up, down. So this is just a compare between adjacent elements, and then so this is up and down. So now looking at those together, this is a Bionic sequence. Now you do a compare so that you end up with two Bionic sequences, but this one is smaller than this one. Okay, and then you order within these subsequence of size 2. And so what you have now is you have a Bionic going up and going down. Okay, so this is a larger Bionic. Okay, so you see, you start with just two elements. And then, so yeah, initially just two elements. So then you have like basically 4 Bionic sequence of size 4. Okay, and now you have Bionic sequence of size 8. And then again, you are going to compare. You get two subsequences. This one is smaller than this one. You can just sort. Okay, and now you get this Bionic sequence of length 16. Okay, and so the idea is you start with small Bionic sequences and doing this business. You keep getting larger and larger Bionic sequences until the whole thing is just sorted. Okay, and each step here is basically log n. And then you increase the size. So every block, you have log n of these blocks. So basically log square n passes, okay, which is super fast if you have enough computing units. Right? And everything is completely regular. You see that, so it's shown in this manner because you can build hardware that basically does this communication extremely fast. You can figure out what sort of network and how to exchange data to make this super efficient. And it's exactly the same thing no matter what the input is. So it's very, very special in that sense. Okay, so so before doing the exercise, just going to show you this demo. So Python code, I'll just skip that because we're going to do the C++ code directly. So it's actually quite difficult to picture, but you're going to get Bitonic sequences are larger and larger. And they tend to be inverted. So, right, it's actually a little tricky to see, but this one's going up, down, and the one wants to go down, up, and they just keep going like this. And so, for example, you're going to take this Bitonic sequence, and then you're going to sort it. Take this Bitonic sequence, you're going to sort it, and then this is going to create a larger Bitonic sequence. Okay, so you can see that. So now you're doing the larger passes to sort. Right? And one more is going to be sorted. And so, right, this guy is sorted now. This guy is sorted, so now this is a larger Bitonic sequence, and this is a larger Bitonic sequence. So you're going to take that one now, sort it. So, you know, it's going to go up or down, I'm not sure. Okay, and then this one, you know, sort it, and then you're going to get, you know, this larger Bitonic sequence and so on. Right, so now it's going to sort. It's going up here, and then down there. So you're on your way to getting, you know, Bitonic sequence of size over 2. And they are sort of opposite of each other, and now you can again sort each Bitonic sequence. So you get a huge Bitonic sequence that finally gets sorted. So, by the way, if you look here, you can see that, you know, how this is sort of similar and different from Mergesort. For example, you know, when you have a Bitonic sequence, you're going down and up. So at some level, you're dealing with two sequences that are sorted. So, you know, you could do a Mergesort if you wanted. But the advantage of doing this is in the Mergesort, again, you know, you have these pointers that move and so on in this irregular fashion. So, you know, in terms of hardware, you know, the calculation is hard to optimize because, you know, you have this uncertainty as to exactly how these pointers are going to operate. Whereas here in these log n passes, everything is completely deterministic. You always do the same comparisons of essentially the same memory locations. Because the actual data varies, but the memory locations, the addresses and so on, you know, it's always the same. So you can go higher and so on, so that you can make these comparisons very efficient. So now this is the smallest level. Well, next one is smallest level sort. So now you okay. What is this now? Oh yeah, right. This is the same thing, but like way more. Again, let's skip that. This is like way more entries. Okay, so so now if you can open up your computer, yeah. So okay, so you know, not going to have enough time for this, but well, I put as many instructions as possible in the slides, so hopefully it makes sense. Well, you know, I'd like to at least go over the main ideas of how to implement this, and then hopefully you can get started. Well, the solution is here, so you can definitely, you know, work on this after class to see how this is done. So you have to start with Bitonic sort lab, okay, and you should be able to compile and run the code. So it should run correctly, but it's not parallelized, so there's no OpenMP in it. Okay. So so just some information. Well, there is this option that so by default it's actually sorting a fairly large array because it's how you can get performance and see speed ups. But if you remove this n-debug from the make file, you're going to be sorting a much smaller array, and it will print some information. But at some level, it's not super useful really for this this exercise. So you can keep this no debug option. I think you should be fine. But just to kind of explain what this is doing. Okay. So now, if you can open up the code, right? And so actually, I'm going to let's see. So actually, I'm going to open the code right here, probably. Maybe the easiest. Stanford, where is it? Right here. Boom. So I'm going to open up the lab code and kind of show you what we're talking about. So this is the lab one. Okay. So it has actually a little bit of OpenMP in it, but it's just to print the number of processes and so on. You know, so it's just so you can vary the number of threads with this. So in terms of benchmarking and testing the gains that you get from multiple threads, you can run your code with different exports. And this is just to check that this is correct. So there's later on we're printing number of threads being used. Okay, so here this will be used later on. Okay, so it starts here. So this is the first bit. And so the loop over I is basically the size of the Bionic sequences you're playing with. Okay, so initially you start with just very small Bionic sequences. You have a lot of them, and as you go, you have fewer and fewer Bionic sequences. Okay, and each Bionic sequence is being sorted independently. Okay, so for example, if you look at the I loop cannot be parallelized. Okay, the next iteration depends on the previous ones, and the thing you can do here. But the J loop, that's independent. So first step is to pragma OMP parallel 4 on the J loop. Okay, so let's start with that. So you take the J loop and you add a pragma OMP parallel 4 in front of the J loop, compile, and that should take care of the first step 1, parallel to J loop. So you keep the sequential Bionic sort inside, but just put a pragma parallel 4 before the J loop. So let me know when you have this working. So as usual, you have to adjust the makefile, pick your compiler, your options.
The Bionic sort lab file?
Right, the lab file. So the sort is the solution. The lab file is the one you have to work with. Well, you can peek at the solution. Well, initially, the first step is going to be easy, so you should be able to do it. After that, it gets increasingly more challenging. The I loop is basically the one sequential, right? You have to wait for the previous I before going to the next I. So here there's nothing you can do because this is the length of the Bionic subsequence. But the J is working, each Bionic subsequence that's independent. Okay, so you can just do pragma OMP parallel 4 on the J. Okay, so you're good here. Yeah. So you're good compiles, yeah. It's just.
That's it.
Yeah, so it's the first step. It's not that simple. Okay, so let's continue. First step is just adding a pragma OMP parallel 4 right here. Okay, so yeah, it's 44. So what's the problem with this strategy? Okay, well, the question is basically how long is the J loop? Okay, so let me maybe zoom a tiny bit more. Okay, so the J loop goes from 0 to n, but it's steps by I. So basically, the J loop is it's operating on a Bionic subsequence, and I is the size of a subsequence. Okay, so you're just jumping by I. Okay, so this is fine, but I keeps increasing. You start with very small subsequences. You keep multiplying I by 2. So J plus equal I. This is larger and larger. So you have fewer and fewer iterations. So at some point, you're going to reach a point where you do not have enough iterations to keep all your threads or cores busy. Okay? So what do? Okay, so now you need a different strategy. Parallelizing I not possible, parallelizing J not possible, so you're going to need to parallelize this bit here. Okay? So what I want you to do is you're going to copy and paste this I loop, and you're going to go from up to chunk, which was computed previously. Okay, so basically you're going to go up to a certain size with a pragma MP parallel 4J here, and then you copy the second loop a second time where you go from chunk to n. Okay, now this loop is too small, so no pragma here. Here you're going to call sort par, and then you're going to be working on par to make that routine parallel. Okay, so actually the par is already there. I mean, there's it's just a copy of sec, so in some sense there's nothing in it. So you have sec, which is sequential sort. You have par, which right now is just the same thing, but we're going to be working on basically parallelizing par. So the nice thing is, basically the way this works is that when this loop is very small, it means you're working with very large chunks. So actually that routine becomes very parallel, right? So it's kind of one or the other. Either you have many chunks and you can work on them in parallel, or you have few chunks but they're big. So there's a lot of parallel work inside each chunk. Okay. So second step is you essentially copy and paste the I loop. Okay. So basically just like this. Copy and paste the I loop. In the first one, you have a lot of chunks, so you keep the OMP parallel 4J. In the second, in the second block here, you're going to call the Bionic par. Okay. So you don't parallelize the J loop, but you call Bionic par inside. So just copy and paste. So I don't know what to do with time. It's 47. So. Okay, so here, maybe I'll just show you the solution to kind of show you what this is supposed to look like. So I can go here. So basically, I sort of showed you what needs to be written. So you have this I loop here. You stop at chunk, and then just basically copy and paste, but starting at chunk times 2 up to n. Right? So it's basically splitting the loop into part 1 and part 2. Okay, so you stop. The first one stops at chunk. The second one restarts at chunk times 2. So this is what you're seeing here. Okay, so here you pragma OMP parallel 4. Okay, so let me, in just of time, continue. So now we skip parallelizing the J loop. Okay, so J loop is just normal, sequential. And then you call Bionic sort par instead of Bionic sort sequential. Okay, so what's happening again is the J loop is very short, but I here, which is the size of the chunk, is very large. So there's going to be a lot of parallel work inside Bionic par. Okay. So now let's go down in Bionic sort par, see what's happening there. Okay, so this is Bionic sort par, so it's actually the same as sec, just copy it, and now the I loop is very, very long. Okay, so this I loop is basically doing the compare, and it's working with a very big chunk. Okay, so essentially split length, okay, which is basically n over 2, or it's basically I over, the previous I over 2, so it's the length of the Bionic subsequence divided by 2. So this is very long, so you can just say pragma MP parallel 4, because this is just a simple comparison. This is the coex operator. So this can be completely done in parallel. You're just looping through I, everything is independent, and so you have pragma MP parallel 4. And then once you're done, so actually the original code just has these two things. So you can start with that. That is the next step. Then I'll explain what happens with the last bit. Okay, so right now it's just basically parallelizing the I loop. So you do pragma MP parallel 4 in the I loop inside Bionic sort par. Okay, so copy the I. Okay, so basically it's, we're doing, the first part is, I going from 0 to chunk, and then the second part is chunk times 2 up to n. Okay, and so what's happening is here you're working on very long, very big chunks, so the compare step, which is the Bionic par, can be parallelized. So you're going to parallelize the loop over that. So this is the second pragma OMP parallel 4 that's inside inside Bionic sort par. So okay, so this is the second loop. Okay, from chunk times 2 to n, you call Bionic sort par. So I already showed you that. And then inside Bionic sort par, okay, the I loop, which is basically the compare loop, is very, very long. So this is the length, or split length, is very large. And all these steps are independent, so you can just add a pragma OMP parallel 4 in front of this I. And there is one more difficulty here. Right. Okay, so the difficulty is that difficulty is, here's what happens. If you look at how the code works, is you make these, so let's go down to sort par. Oops, sorry, it was just right here. Right. So inside sort par, you just call yourself with a sequence of size half. So you go, n over 2, n over 4, and so on. So at some point, split length again becomes too small. So I need to wrap it up here. 52. So at some point here, the split is too small. So here, I'll just give you the solution, but you have to think about it. So what's happening is, there's not enough work in Bionic sort par when this becomes too small. Okay. So there's an if statement, okay, that you keep calling yourself recursively until split length becomes too small. So you stop before the end, okay, and this is equivalent to basically, when you do one of those, it basically means you do a couple of steps and then you stop, okay, and now you go back to the outside loop and you finish off by parallelizing, over the sequences again, okay, because essentially the compare becomes too small. But again, you go back to having a lot of chunks. So you can go back to sort of your original strategy. So that is trickier to figure out. So I'll let you think about that. So I need to wrap it up. But there is this condition. So essentially, we have unfinished work. And this is done right here. Right? So here, this was your sort of original code. But because you have unfinished work, there's just a little bit that needs to be done here. But since we're working with a lot of chunks, okay, then you can go back to the original strategy of OMP parallel 4J. Okay, and then that's it. So we go back and forth between essentially either having a lot of chunks and you parallelize over the chunks, or having few chunks but very big and doing the compare in parallel. Okay, and so you have to sort of keep going back and forth with these two strategies to get good parallelization strategies. So you can see that it's all pragma OMP parallel 4, but the algorithm itself is not that straightforward, okay? And so this is explained here. Go back to loop I and you add this little bit to finish off the work. Okay, so we can look at the solution here. And this is the timing, for example, I got on Google Cloud. So running one thread, 3 seconds, running with 4 threads, 0.8 second, which is pretty much exactly 4 times faster, so very nice speed up on, so as you go closer to 8, then the speed up sort of tapers off a little bit. You get a little bit less benefits, but at least initially, 1 through 4, you really get full speed up with this multi-core implementation. Okay, all right, so wrap it up here. So essentially, this completes all the stuff about C++ threads, OpenMP, and so on, all the shared memory discussion. So this is the last lecture on that. And so starting next week, we're going to be talking about CUDA and how to program NVIDIA processors. So we're going to have finished by the NVIDIA guest lectures, and then MPI at the end of the quarter. So if you have problems, compiling and so on, or installing the Google Cloud, we can help you now. If you want to stay around, we can help you, fix your compiler issues. Thank you.